Good evening, students. Today's topic is resistance of a conductor. So let us understand what is the concept of your resistance. It is actually the opposition offered by a material to the flow of electric current through it. So let me explain you from where that opposition is coming from. Let us consider a simple, let's say, iron bar. For that, to know the concept of resistance, you must know the structure of atom, also the structure of solids. We know usually most of the solids, they are crystalline in nature, and crystalline means the atoms in a bulk material, they are arranged in a regular fashion. Let me give you a very simple example. If you consider this room, it's a regular structure. Let's say it's a cube. The room is a cube at whose corner one atom is placed. It's a structure. That is called your crystal structure. It's a simple atomic arrangement. I am talking about a simple atomic arrangement where you consider a cube at whose corner all the atoms they are situated, and the forces between them, they balance and they form a stable structure. So then where comes your resistance? So if you consider a bulk material like this, so there are n number of that similar kind of cubes at whose corners atoms are located. So when the atom gain thermal energy from outside, because of the fluctuation in the temperature, they gain thermal energy from outside world. Clear? Apart from that, current flows through a conductor when you apply electric field across a conductor. So when you apply electric field, that field influences all the atoms, they are placed at the at the corners of your lattices. That structure is called your lattice. The simple cube what I have considered, that is called a lattice. Clear? So the electric field which is set up inside the material, or that means because of the potential difference, the created potential difference by the means of a battery, when it is connected across the solid or bulk material, then it vibrates all the cubes, means that is called your lattice. The lattice will starts vibrating. Clear? And you know, in a metal there are large number of free electrons that conduct electricity. Electrons are negatively charged. If one electron is left out from an atom, that atom becomes your ion. You consider there are ions, lattices of ions. Lattices means it's a definite arrangement where all the ions are placed inside that bulk material. That a regular fashion is repeated to have this bulk material of conductor. So when you set up electric field, that structure, that lattice structure, it's vibrating vigorously. Means structure is also, means there are n number of cubical structures. If they vibrate, the space between them, space between the atoms, it fluctuates. When an electron moves in and around, electrons are there negatively charged. When there is a lattice vibration, so what it will do, it will just try to deviate the electron from its path, because the nature of the intermolecular forces is disturbed. So the flow of the electron is not smooth in this case. So in this case the electron flow is not smooth. So it find as if something is pulling or pushing or in sideway, in forward directions. It's a kind of your that is the concept of your resistance or oppositions. Clear? So basically, because of the electric field that is set up across a conductor, also because of the thermal energy, lattice vibrates, and lattice vibrations along with the influence of the field produces the resistance. That is a microscopic cause of your resistances. Clear? Then we will see what is the unit and dimension of your resistance. We know that the resistance is given by V by I from your Ohm's law. So here the unit of V is volt, unit of current is ampere. So volt per ampere is the unit of resistance, and 1 volt per 1 ampere, it is 1 ohm, which is the unit of your resistance. This is the symbol of resistance, ohm. You can find the dimension here. So resistance dimension you can find the dimension of V and dimension of I. Dimension of V you can find from this equation. W is equal to VQ and V is equal to W by Q. So W means work. Dimension of work is, so you can write down W by Q. Q is equal to your current into Q is equal to dimension of Q is A into T, and or you can simply write the equation Q is equal to I into T. So now I can substitute this equation here to find the dimension. So V is equal to W by IT, and here it is 1I, W by I square T. So W dimension is M1 L2 T minus 2 divided by I is your A2, T is T1. So if you simplify, your dimension is, which is M1 L2 T minus 3 and A minus 2. This is the dimension of your resistance. Now let us find what are the factors on which resistance depends. So let me explain once again. The concept of resistance is because of the vibration of the lattice in a material, yes, and because of the thermal agitation produced by the thermal energy and because of the temperature fluctuations. Because of that, when the electron flows through the conductor, it experiences that resistances or the opposition. Clear? Because it's an interaction of the electric field inside. Because of that reason, the resistance comes into picture. Now let us see what are the factors on which the resistance depends. Suppose you have a material whose length is, you have a conductor whose length is L and area of cross section is A. Suppose you have a conductor whose shape is like this. For simplicity, its area of cross section is A and whose length is L. Factors on which R depends. Suppose the temperature of that material is fixed. It is fixed at a particular point. So at a particular temperature, the resistance is directly proportional to the length of the conductor. Means, if a charged particle will start flowing from here to here, if the length will be more, then when an electron is moving through a conductor, because of the lattice vibration, thermal vibration, it collides with the lattice wall, also with themselves. And remember that collision is not like your physical collision, like physical contact of electrons is not there. It's a collision of the field, we can say. Clear? So because of the collision, that opposition is coming to picture. So that opposition is your resistance. So if the length of a conductor is more, then the number of collisions suffered will be more. So the resistance will increase. Clear? And if the area of cross section is more, the resistance will be less. From a common sense, because if this area of cross section will be more, then the electrons will find more area to pass through, so the number of collision per second it will reduce. Clear? So that's why if you combine these two, R is given by a constant rho L by A. Clear? Here rho is called a specific resistance or resistivity. Here R is equal to rho L by A. Here rho is called resistivity or specific resistance, and from here we can write rho is given by RA upon L. So from this equation we can find out the unit and dimension of rho. The dimension of resistance is ohm, area is meter square and L is meter. So meter square divided by meter is simply meter. So your unit is ohm into meter. Clear? And symbol is ohm into meter. That is the unit of your resistivity. Now we can find the dimension. So the dimension of R, what we have found, dimension of R, it is W by I square T, which is M1 L2 T minus 2 by a square, I is equal to a square, T is your T here. So in that case, you see, you can find the dimension which is M1, L2, T minus 3, A minus 2 is the dimension of your resistance. And dimension of resistivity is what? Dimension of resistance multiplied with the length, because area upon length you will be getting only length. So the dimension of resistivity would be simply you can write it, which is M1 only multiply 1, so it is L3, M1 L3, T minus 3, A minus 2 is the dimension of your resistivity. So just remember here this is the dimension of resistivity. Now sometimes it will be asked to find out the define what is the meaning of your resistivity of a particular material. So if you from this equation, if you take A and L to be one unit in a particular under particular system of unit, so you will find rho is equal to R. Rho is equal to R only when A is equal to 1 unit. So under SI system is your A will be 1 meter square, L is equal to 1 meter. So in that case, whatever be the resistance suffered by the material is called your resistivity. So let me define you. Suppose you have a conductor whose cross-sectional area is 1 meter square and the length of that conductor is 1 meter. Suppose you have a conductor whose cross-sectional area is 1 meter square and the length is 1 meter, then that particular conductor of a particular material, it has some resistance. That resistance, that value of the resistance is nothing but your resistivity. Clear? Suppose you have an iron bar whose length is 1 meter, area of cross section is 1 meter square. Then you can find out the resistance of that iron bar. Whatever be the resistance, that is called your resistivity. So here you try to understand there is a most important point here. See, at a particular temperature, the resistance depends on the shape and size and the temperature of that material at that particular point. Clear? So resistance depends on the shape and size of the material, and also it differs from material to material. Clear? But resistivity, it only, suppose resistivity, it is a constant for a given material. That's the most important point. Let me explain you by taking the example. Suppose you have a copper wire. Suppose you have a copper wire and you have one iron wire. Got? So copper wire and iron wire, since the nature of the material are different, their resistivity are different. Copper and iron, their resistivity are different. So also their resistances. See, suppose you have a copper wire, the area of cross section of copper wire and the area of cross section of your iron wire, both are same, length are same, their resistivity and resistance, they will be different. Second example, suppose you have a copper wire whose length is, let's say, 1 meter and another copper wire having same cross section whose length is 0.75 meter. You see, as the resistance depends on the shape and size, these two materials both are of copper, this is of copper. Both are having resistivity same. Rho same for both these materials, but resistance of these two materials, they are different. But R is different. That's the point of summary there. See, R depends on the shape and size. Here the length is more, so resistance is more. Here the materials are same, both are copper, so resistivity is same. That is the point there. And also you see, the resistance depends on temperature, and the equations are like this: R is equal to R naught 1 plus alpha delta T, and resistivity rho T is equal to rho 0 1 plus alpha delta T. Delta T is the change in temperature. R0 here, it is the temperature, it is the resistance of a particular conductor at 0 degree. So also the resistivity here. Here rho 0 is the resistivity at 0 degree Celsius and delta T is a change in temperature. Here alpha, here it is called the temperature coefficient of resistance, and here this alpha is called temperature coefficient of resistivity.